Hey guys, here we are at the end of spring break. Time to get back to the grind. So this is our first video after spring break. Is counting and probability, including independent and dependent events. So of course, we've had everything to do in these last 2 days of the break, including lots and lots of this stuff right over here. Yeah, this awful stuff in here. Yeah, laundry. So this is kind of cool. You know, the infinite love, infinite probability that anything's possible, basically. Someday this is going to happen. Hopefully it's in my house. Okay, so what are we talking about here? We're talking about counting, which involves finding the number of possible outcomes a particular set of events might have. And I know you're thinking when you saw that in the title, like counting? Like I already know how to count. Right, but this is actually finding the number of possible ways something can happen. And it's actually the very first thing you talk about in a basic computer science course. So this is the branch of math that makes it towards computer science. Because when you actually look at the way a web search engine works, and this is such an oversimplified way to put it, so you'll have to learn more on your own if you want to understand better, but basically what it does is it searches for the very specific set of inputs or sequence of letters that you're looking for in all the different possible sequences of letters that are out there that are possible. And so it has to count those first before it can find where that is. Again, super oversimplified view, but hopefully you get the idea that this is the kind of stuff you might want to learn if you want to learn computer science. Anyway, that's counting, and we'll talk about some more about counting in a minute. Probability is the branch of math that studies the likelihood of particular events or combinations of events. And the probability of an event is measured on a scale from 0, meaning impossible, like right here, impossible, not going to happen. Easter's on a Tuesday. Snow on the 4th of July. Actually, that's probably not impossible, but probably pretty darn close. Anyway, snow here on the 4th of July, to 1, which is certain, which is definite, like Memorial Day on a Monday, because it's a Monday holiday, or that you're going to do this video for homework when it's assigned. Oh, I wish that was a probability of 1. Anyway, when you express that probability, it can be expressed as a fraction, a decimal from 0 to 1, or a percentage from 0% to 100%. And there's a spectrum of probability. Some things are extremely unlikely, some things are very likely, and sometimes you can actually calculate the exact probability of something. But before we do that, let's talk about the fundamental counting principle. The fundamental counting principle states, if event 1 can happen in m ways, m representing a number, and event 2 can happen in n ways, again, n representing well, possibly the same, but another number, then a combination of the two events can happen in m times n, or mn, algebraically, ways. So that means we can multiply those two possibilities, numbers of possibilities, to find the total number of possibilities. Example, Jesse can choose from 3 dress shirts, 4 pairs of pants, and 5 ties for his school picture day. How many outfits are possible? So first of all, there's a glaring grammatical error here in punctuation and capitalization. This should have been a period, and this should have been a capital H. So, shirt, pants, tie. Of course, he has other things he's gonna wear, but those are the main things here. So 3 different shirts times 4 different pants times 5 different ties. There is a possibility of 3 times 4 is 12 times 5, 60 different outfits. Now I know that doesn't mean all of them will match, but let's just pretend he's a stylish guy, so everything would basically match. So 60 possible outfits, because the fundamental counting principle has us multiply those out. Now I could very well make a tree diagram for this, where I could take and we've got the possibility of 3 dress shirts, and then I could bounce off of that. Every one of those has 4 possible pants, and then every one of those would have 5 possible ties, but as you can see, that would take a long time, and I don't actually need to know what those combinations are. I just need to know how many combinations there are. So that's the fundamental counting principle, and that is quite useful as a mathematical concept goes. Okay, the probability of an event is the next thing we're looking at. The notation here is P and then the parentheses, and then whatever the event is in parentheses. And we find that probability by taking the number of favorable outcomes for our event and dividing that by the total number of possible outcomes. So you're going to express that answer as a fraction in simplest form, or as a decimal, or as a percent, like we expressed in that definition slide. So here's our example. Crystal chooses a card at random from a standard deck of cards. What is the probability that she will choose a diamond? Okay, so we would write that, first of all, as the probability of choosing a diamond. Or you could actually draw the diamond. You could do that with a little red. There we go. Diamond. All right. The probability of that, well, that's going to equal the total number of possible outcomes, which is 52, and the number of diamonds there are in the deck, which is 13. Ace all the way through king of diamonds. And if you simplify that, you're going to get 1/4, which would make sense because 1/4 of the cards are diamonds, because there are 4 suits in the deck of cards. And when you talk about decks of cards problems, never include jokers. Jokers are not really part of the standard deck of cards. When we talk about a standard deck of cards, we're talking about ace through king of each of the 4 suits. All right, and I could express that answer actually in 2 more ways. Let's do that. So as a decimal, so this is a good chance to review our fractions, decimals, and percents. As a decimal, it would be 0.25, and as a percent, it would be 25%. So I have a 25% chance of choosing a diamond if I pull a card at random from a standard deck of cards. All right, so we'll try some of these. The first 2 are done for us, so let's go over those real quick, and then you can pause it and try these on your own. What's the probability that a 5 is rolled on a number cube? Well, a 5 only happens in one of the ways on a single cube, and there's 6 possible outcomes, so that means we would have a 1 in 6 chance of getting that on a number cube. And we won't worry about the percents and the decimals. If you want to go through and do all of those on your own, you're more than welcome to. All right. So find the probability that a number greater than 6 is rolled on a number cube. Well, if there's no numbers that are greater than 6 on a number cube, then that would be 0 out of 6, or just 0, because it's impossible. All right, so why don't you pause it and try these problems here, and I'm going to go ahead and do the same thing, but I'm going to go ahead and put my answers in for each one, and you can see how you did once you are finished with them. But I do really advise you that you actually do pause it and try them, rather than just watching. Okay, pause it, please. And here are your answers. All right, and after double and triple checking my answers, here you go. So in this one, you've got the slips of paper 1 to 20 written on the slips of paper. You draw one from at random. What's the probability that's less than a 5? Well, the possibilities there are 1, 2, 3, and 4. So there's 4 possibilities out of 20, which simplifies to 1/5 or 20%. A number ends in 5. Well, there's only 2 of those, 5 and 15. So that's 2 out of 20, or 1/10 or 10%. The number's even. Well, from 1 to 20, that is half of those are going to be odd and half of those are going to be even. So 1/2, or 50% if we're going to continue with the percents. For this one, the number is divisible by 3. Well, we counted that up. So 3, 6, 9, 12, 15, 18. So that's 6 possibilities out of 20, or 3/10 or 30%. That the number is prime. Now, this requires you to go back and know your prime numbers. It's a great way to review that concept briefly. 1 is not prime, so 2, 3, 5, 7, not 9, so 11, now we're up to 5 numbers, 13, 17, and 19. So it's a total of 8 prime numbers out of 20, and 8 out of 20, when you simplify, dividing both by 4, you get 2/5. The digits having a sum of 10, the only ones are 1 and 9, because that's 19. 19 would be the only number where the digits have a sum of 10, so there's 1 out of 20. I caught that mistake my first time through checking. The number is less than 25. So this one, that's either a 1, if you want to express like as a fraction, we wouldn't put 1 over 1 or 20 over 20, we would just write 1, or 100%. So that's a definite one, that's certain. All right, the number contains a 1. So that would be the number 1, the number 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. And that's a total of 11 possibilities out of 20, which cannot be simplified. In the next section, you have numbers of marbles. We have 5 purple, 7 gold, and 3 red marbles in a bag. That's a total of 15 marbles. So we need that number in order to continue with the problems. So that's the first thing you would have identified had it not been something like this one where it's actually just written out. So 15 marbles. So what's the probability of getting a gold marble? That's 7 out of 15. Cannot be simplified. A purple one, 5 out of 15, 1/3. One that's red or gold. Add the red and the gold together. So 7 and 3, 10 out of 15, 2/3. Not red. So take away the red, which is taking away 3, not 12, which I started to write in the first place, but 3, and you get 12 out of 15, simplifies to 4/5. Okay. Moving on to the probability of multiple events, more than one event happening at a time. That's so that you're finding more than one event, and they are either going to be independent or dependent events. Two events are independent when they have no effect or influence on one another. That's a with replacement problem. So when two events are independent, they have no effect on each other, or we're talking about a situation where you pull like a card out of a deck and then you put it back before you pull another one. Two events are dependent when the second event depends on the first event's outcome. This is the without replacement type problem. So this would be like having that deck of cards, pulling a card out of the deck, not putting it back and pulling another card. That would influence the outcome because now you have less cards to pull from. And if the probability is favorable outcomes out of total, then clearly less outcomes means it's going to change what the probability is. Okay, to find independent events probability, multiply the probability of each event and simplify. So you multiply, express your answer as a fraction in simplest form. So the probability of A and B is the probability of A times the probability of B. All right, example. Find the probability of pulling a diamond from a deck of cards and rolling an odd number on a die. Well, we expressed earlier a diamond from a deck of cards ended up 1/4. Or 13 out of 52. So we simplified to 1/4. An odd number on a die. Well, a die has 1, 2, 3, 4, 5, and 6, half of which are odd. And when we multiply, we get 1/8. So you have a 1 in 8 chance of having both of those things happen when you pull the card from the deck and you roll the die. Now the probability of dependent events. So the probability of A and B when they are dependent, oops, didn't mean to write there. Here we go. There we go. Is the probability of A times the probability of B after A has already occurred. Or that can be written the probability of A times the probability of B after A. And so what this means is when you find the probability of B, you pretend that A has already happened. So if it's a card out of a deck, you pretend that card is gone. Or if it's a marble out of a bag, you pretend that marble is now gone. And so it changes the overall makeup of what you have when you find the probability of the second event. Again, you're going to multiply. Again, you're going to express your answer as a fraction in simplest form. Find the probability of pulling two diamonds, should be an S on the end of diamond, in a row from one deck of cards without replacement. Well, we already know the probability of pulling one diamond is 1/4. Now, pretend we have now pulled the diamond out of the deck of cards. Well, the first thing that's apparent, the first thing we have to think about is that we no longer have 52 cards. Now we have 51 cards. So that's a big change. We also no longer have 13 diamonds. Remember, this 1/4 came from 13 out of 52, which simplified to 1/4. We no longer have 13 diamonds. We now have 12 because we took one diamond out. Again, we are pretending that event A, pulling a diamond from the deck of cards, has already happened. Now I can simplify because when I multiply fractions, I can simplify nicely here. I'm going to divide both of these by 4, which makes my life a whole bunch easier. Okay, so dividing by 4, we now have a 3 up top and a 1 down on the bottom. Multiply across the top, we have 3 over 51. Now that can be simplified. That's something to be real careful about. Remember to use your tricks for divisibility. Add the 5 and the 1 together, you get 6. That means it's divisible by 3. It's 17. So it's a 1 in 17 chance that you're going to pull two diamonds in a row without putting the first card back. Okay, so here's a couple of problems to try. What I want you to notice is that one section here is a with replacement situation and one is a without replacement situation. So one is independent and one is dependent. And start off by reading the directions for both sets and identifying that first. Then pause it and try the problems. Okay? Okay. All right. Well, here come your answers. Okay, going over this is going to wrap up this video, and it's all done for your first back from spring break. Okay, so got a deck of cards 1 through 10. We are picking a card from that and tossing a die. Clearly independent events. So this was your independent events section, and making that your dependent events section. Okay, so a 10 and a 3. So a 10 from this deck of cards would be a 1 out of 10. And a 3 on a die would be a 1 out of 6. Multiply that 1 out of 60. Can't be simplified. 2 evens. Well, 1 through 10, half of those are even. 1 through 6, half of those are even. Half times a half is a fourth. 2 prime numbers. So we can list out the prime numbers between 1 and 10. That's 2, 3, 5, and 7. So 4 out of 10, which I simplified to 2/5 before I started the problem. And then the primes between 1 and 6 are 2, 3, and 5. So that's going to be 3 out of 6 total, which I simplified to 1/2. Multiplying across the top and the bottom, you got 2/10, which again simplifies one more time to 1/5. 2 odd numbers, it's the same as 2 evens. Half and half, 1/4 when you multiply. An even and a prime. Well, the prime for the second one happened to be 1/2, and even for the first one happened to be 1/2, still 1/4 for second answer in a row. A 7 and a 5. So a 7, there's only one card with a 7, so 1/10. And a 5, there's only one number on that die. That is a number 5. So a one side that is a number 5, I should say. So again, like the first one, that's 1/60. So in this one, we got 4 red pencils, 5 green pencils, and 5 yellow pencils. Once a pencil is selected from the jar, it is not replaced. And I guess we're pretending we can't see the colors and we're not just picking a color. So first thing I did was add it all up. There's 15 pencils there. So a red and a yellow. So a red is 4 possible out of 15 total pencils. Now, pretend I've now taken out a red pencil. I don't have 15 pencils anymore. Now I have 14 in there. So let's change this number. Now we're looking at yellow. Well, there's still 5 yellows like it says at the beginning. And then I could simplify. When you multiply fractions, you can simplify. So I can divide the 5 and the 15 both by 5, leaving a 1 and a 3. The 4 and the 14 both by 2, leaving a 2 and a 7. Multiply across the top and the bottom. Can't be simplified from there. 2 green, 6 out of 15. And then there's 1 less green, so it's 5. And there's 1 less pencil, so it's 14. Multiply, simplify, comes out to 3/21. And simplify again 1/7. For this one, again, green, 6 out of 15. After you pull the green one, now you have 14 pencils, and you have 5 yellows, so green then yellow comes out exactly the same as 2 green in a row. And that, my friends, is the end of our first video back. Starting to lose my voice already. Not used to doing this at all. I'll see you guys in class.